We're going to take a particular focus today on optimizing costs and also management best practices for containers with shared file storage. And I'm going to unpack a little bit as we go here. But first and foremost, what we want to talk a little bit about is how do we really think about containers when it comes to cost optimization, when it comes to efficiency management. What are some of these broad subjects that come up oftentimes for customers that we can help with in terms of letting things run more smoothly and more operationally efficient? And then some of the current trends that we see with containers. What are we seeing out in the marketplace today? And all of that is going to lead us into a conversation around stateful applications and really around storage. And so we're going to talk about some cost efficiencies with Amazon EFS. I'll also cover a little bit with FSX. And then I'm going to spend a little bit of time demoing a solution for you to give you a picture of operationally what things might look like using one of these shared file system solutions in an Amazon EKS Kubernetes environment. And then we'll wrap things up with a call to action. All right. So with that, let's talk a little bit about containers. So workloads that run in modern applications running in containers have a variety of dimensions associated with them. So at the very kind of basic level, we have the infrastructure component. And as one might imagine, that usually is broken down into a few different aspects. So we've got compute, we've got networking, we've got the storage piece of that. From a platform perspective, customers that are running modern applications in containers on AWS have a variety of choices. The most common one that we see today is Amazon EKS, which is our Elastic Kubernetes service. We also have a lot of customers running containers in Amazon ECS, or the Elastic Container Service. And those are for customers that want to be able to take advantage of containers and microservices without any of the management overhead of Kubernetes, and they want a simple way of deploying and managing containers at scale in a fully managed service. And lastly, we have our Elastic Container Repository, which is for image management that's part of the overall solution stack. There's a couple of additional ways that customers run containers today in AWS. Some of them kind of run their own container orchestration platform on top of EC2. So we'd call this a self-managed solution, whether that be Kubernetes or another containers solution that would be self-managed. And then we also have customers running things like Red Hat OpenShift on our fully managed Red Hat OpenShift on AWS solution, or ROSA for short. So just to kind of round out some additional things that people do. And then with that, we have a variety of tool sets that augment and enhance the overall management experience. So from a DevOps tooling perspective, we have solutions around security, CI/CD pipeline management, and then observability tools for logging and those sorts of things, which we'll look at a little bit here. And as we're having a conversation about optimization, we don't want to neglect one of the most overlooked areas, which is the operational cost associated with managing these modern application stacks. Oftentimes, what we see is customers that are running their own containers orchestration solution have a lot of management overhead in the cost of engineers and DevOps people that are having to manage infrastructure. And we really want to help by taking away some of those undifferentiated heavy lifting activities and moving that into managed services so that end users can really focus on what is going to bring the most value to the business. And oftentimes that has to do with deploying code and maintaining code so that our applications run smoothly. So let's look at some usage trends. I put this up here because I think it's really important to understand. I've been in the industry for about 19 years now, and I remember back in the early days of my career, there was a lot of hype around consolidation, and virtualization was a somewhat new concept in the industry. And we were seeing mass reduction and in terms of waste, and also increase in efficiency by using things like VMware and different virtualization tools that allowed us to get better utilization out of our applications. And the same is actually true now as we're looking at a world that kind of runs on microservices and containers and things that typically run in a very small fractional resource utilization. Oftentimes what we see is that we still find a lot of waste from the perspective of CPU and memory. As we're provisioning resources, we want to make sure that we have enough available, but unless we're using tools and automation to really optimize the use of those resources, we can find that the spend that goes into maintaining these infrastructures can start to snowball. So we want to look at ways to optimize that. So as you're running your containers in AWS, there's some things that you can do. I mentioned some of the analytics that we have for monitoring and logging. So with CloudWatch, we have the ability of getting some good statistics around utilization for CPU, for memory, and for even network. What's missing here, you might notice though, is there's nothing here about storage. And we'll talk a little bit about the importance of storage and the role that that plays in modern stateful applications and the trends that we're starting to see more and more prevalent across the industry, and why it becomes really important when we're making key decisions around infrastructure, around persistent data and storage. So again, when we're talking about optimizing for cost as well as performance, there's several dimensions that go into this equation. So from a performance perspective, if we're talking about CPU, if we're talking about network, there's some things that we can do and some techniques we can use to really optimize those expensive compute resources. Things like fractional computing. We have the ability of running serverless workloads. We can use things in EKS like Carpenter so that we're scheduling only the amount of instance resources that we really need to run active containers within the environment, and use auto scaling and different capabilities to grow and shrink the compute resources as necessary. So we're always cost optimizing, but also maximizing for performance without compromising on what the application needs. The same would be true of capacity when we talk about capacity from the perspective of compute. And all of this leads into a conversation around the most value for the lowest cost. And I would submit to you that all of these things are true not only of the compute infrastructure, but definitely true about the storage infrastructure and the data plane as well. So we're going to talk about how to look at that and how to optimize that from the perspective of AWS storage services. Before we get there, just a quick overview again of some of the compute options that we have, and I'm going to use EKS as the example here, and you can change out some of this if you're running ECS or other platforms, but again, EKS is our most prevalent containers orchestration solution, and it's fully managed by AWS. So that control plane that you see there is in its own private AWS VPC. You don't have to manage that as the end user, and that takes away, again, a lot of those low-level tasks that oftentimes consume valuable resources from an engineering perspective, from a DevOps perspective, and allows those folks to really focus on the applications themselves. So moving to the right of the screen here, from a compute perspective, most commonly we see customers still running these compute instances on EC2, but that can be in a couple of different ways. You can self-manage the nodes if you want to have a little bit more control, but again, putting things into a managed node group allow us to have flexibility and use things like Carpenter and spot instances and auto scaling groups to be able to dynamically respond to the needs of the application, rather than having to manually provision infrastructure and manage the growing and shrinking of those compute resources. And then lastly, as I kind of alluded to, for customers that want to go fully serverless, we have AWS Fargate for that serverless experience, where in that case, there's no compute to manage. All of that is managed by the service, and compute is assigned to the pods as needed. All right, so let's talk about adoption trends, because this is going to lead into the conversation about storage and data persistence. So CNCF is really the kind of the leading body that's out there, really giving the industry feedback about what customers are actually doing in the real world, particularly as it relates to modern applications and containers. So they do an annual survey, and we just got the results of the 2023 survey. And they were not all that surprising if you've been paying attention to these reports over the last couple of years. The trends have continued, and we've been on kind of this same trajectory for a little while now, which is the overall increase in adoption, not only of containers for secondary workloads, but really primary workloads and applications that run the business. So if you look at those trends, we can see that of the customers that responded, many of them said that they use them for at least some applications, and even more said they're using them for most or all production applications throughout the organization. So pretty impressive numbers when you think about where microservices were just a few years ago, and people were starting to play with things in development and in sandbox environments, or for those applications that didn't run the business, right? These are the utility use cases where it didn't matter if they were running a container or elsewhere. Infrastructure wasn't quite as important because the business critical stuff was all still running on more traditional infrastructure components. So when users were polled to answer the question, what are your biggest challenges in using or deploying containers? You can see, some of the responses there, and you'll notice storage is down here, and it's not at the top, which doesn't surprise me, but at the same time, that 16% is an interesting number to me. When you think of it, almost 1 out of 5, customers that responded said, yeah, I'm having some challenges managing storage. And I think a lot of that comes down to not necessarily the ease of use. We have CSI drivers now that do a lot of the heavy lifting of that, and I'll get into that in the demo in just a bit here. But I think as we're talking about overall patterns and looking at the cost and the maintenance of infrastructure and the role that storage plays in that, I think it's pretty important to understand that as we see more and more adoption of stateful applications and persistent workloads running in containers, the role that storage plays in that, not only from an operational perspective, but also from a cost perspective. And so we're going to get into that a little bit and talk about some of the mechanisms that we have to offset some of the costs associated with running storage in the cloud for these stateful workloads. And perhaps the most interesting stat that was in the most recent survey is this one here, which is stateful applications. So these are applications that need to have some anchor point of data, whether that would be external to the container environment in some sort of a database or in an S3 bucket, or what we're going to talk about today, which is actually running storage as a persistent volume inside of Kubernetes. And the trends there really speak volumes, I think, if you look at the fact that 82% of folks that were polled said that they're using it in production, or they plan to in the next year, or they're piloting or evaluating. A very high number of stateful workloads that are running out there in real world infrastructures running businesses today. So what are some examples of these workloads? Well, databases are an obvious one, right? We need to maintain state for databases that are running in containers. Developer tools, content management systems, analytics, and machine learning are probably some of the most arguably important and most relevant to what many customers are doing today inside of containers. Again, we've seen this massive shift towards using containers for utility services into business critical workloads, and particularly around data-driven workloads like analytics and machine learning. And that trend is obviously continuing on in 2024 as we see this mass adoption of Gen AI and a lot of interest out in the market and building tools and doing training jobs and inference inside of containers. So why does storage matter? Well, as I said, we've got an increase in these persistent workloads using all sorts of different services that people run in containers. And customers who maybe aren't building applications natively in the cloud, but migrating existing applications into the cloud, oftentimes they have storage associated with those applications. So they need to bring that along with them in order to maintain that relationship in the cloud. And storage can be a significant part of the deployment cost. It may not be the most expensive if you look at kind of the cost of CPU and memory and network, but it's definitely up there in the top contributors in terms of what we pay for to keep these things running. And modern applications rely on storage being not only durable, but highly scalable and highly available. And I'll talk a little bit about the differences of those and how that plays out from a services perspective. So no AWS deck would be complete without the family photo, and this is our current model lineup, if you will, when you think about storage services. So we have 14 unique storage services within the AWS portfolio today, but we're not going to focus on all of these for the context of this conversation. We really want to look at kind of two dimensions, which would be block and file storage. So I'll give apologies to S3. We do have a lot of use cases for S3 in containerized environments, and oftentimes that is deployed by way of API calls, although we do now have the ability of creating a file gateway into our Kubernetes environments by way of a new feature called S3 Mount Point, which we can definitely talk about if that's something that any of you are interested in from a follow-up perspective. But in the meantime, I really want to focus on where I think the biggest opportunity is for customers who are looking to optimize both for cost and performance and enterprise features when looking at persistent data workloads. And traditionally, what we see is this heavy prevalence of block storage when running stateful applications in containers. And from an AWS perspective, that looks like EBS. So many customers are running EBS volumes. And when you create a persistent volume inside of Kubernetes, that persistent volume or persistent volume claim actually creates or maps to a EBS volume running in the cloud in a one-to-one mapping. So you think about one application or one pod in Kubernetes, it's going to get a persistent volume. That's going to be an EBS volume. And that's all well and good, but we have a lot of use cases where that's not necessarily the best strategy in terms of applications that need to either share data with one another, or they need a higher degree of resilience and need to scale across availability zones, or they need enterprise features. And we'll kind of unpack what that looks like. But for the most part, what we're going to spend the majority of the time here talking about is our managed file services from AWS. And I'm going to give particular focus to one in particular. Now, EFS has been in our portfolio for quite a while. It was our first file service that we launched that was fully managed, allowed customers to take advantage of an NFS file share for Linux applications and apps running in the cloud, and was really meant for those use cases, right? File shares. It has some really unique superpowers that I think make it particularly advantageous when we're talking about modern applications leveraging data to either share across container instances or have a high degree of resiliency and durability, and even take advantage of things like multi-region availability and replication. So we'll talk about that. In addition to EFS, we have several offerings of our FSX service, and FSX comes in 5 flavors today, really 4. We can talk about file cache separately, but we have FSX for NetApp ONTAP, we have it for Windows File Server, we have it for Lustre, and now we have it for OpenZFS. And I'm not going to talk in depth about these services today, other than the fact that they are there and bring additional value to these stateful workloads when you're talking about sharing data and having enterprise features. And each of them have kind of their unique use cases and strategies and superpowers that they bring to the table. But before we really get into that, I want to talk about, what about those services that are using EBS today? One trend that I see most often as I'm working with customers is that many of them are being asked to make decisions around storage when they're not necessarily in the business of managing storage. So we kind of have traditional infrastructure teams, we have developers, and in our new modern world, oftentimes developers are being asked to do the jobs of infrastructure people and to some degree vice versa. So we have this occurrence where an application needs to be deployed, it needs to be stateful, and a developer goes in and they say, I need some persistent storage. And they look in EKS and they see, oh, I've got this storage class that's defined for me for EBS. Let me go ahead and consume that. So they'll go ahead and do that. Well, the problem with that is, number one, in the spirit of being backwards compatible, we still have a storage class in our EKS cluster that is built around GP2. And it doesn't mean that you can't use other storage classes. We have the ability of installing the CSI driver and upgrading from older versions of EBS running services like GP2 to more modern versions like GP3 or IO2 or even IO2 Block Express. But again, we have kind of this legacy of developers who maybe, deployed a volume back when GP2 was the best option, or they don't know any differently and they see that that's available to them, so they consume it. So the first thing that I like to highlight is simply by migrating from GP2 to GP3 EBS volumes, customers save around 20%. And this is for a variety of reasons. Number one, we have the ability of decoupling performance from capacity with GP3. And so you don't have to scale capacity in order to get more performance out of those EBS volumes. You can simply provision more performance if you need it. And then from a overall value perspective, the dollar per gigabyte is equivalent and better to GP2 depending on how much data you're putting on it. And there's really no scenarios where GP2 really becomes more cost effective. So first thing that I try to tell customers to do is go ahead and look at your infrastructure inside of your Kubernetes and look at all those attached EBS volumes. And if they're GP2, go ahead and just upgrade them to GP3. And we have a link here to show you how to easily do that in non-disruptive ways. So that's number one. Number two, and this is a real world customer example. I've taken out all the specifics so you can just see kind of the attributes here. This was a customer that I worked with recently, and when we looked at their infrastructure, again, we noticed that all their EBS was running on GP2 volumes. So we definitely talked to them about upgrading that. But we also noticed that a lot of the capacity that they had provisioned was really large. And again, keep in mind that these are volumes attached to individual services or individual pods running inside of Kubernetes. So they're not sharing data. These are unique volumes, but the data sets often do get shared. So in this case, we've got a bunch of very large EBS volumes. And again, because they're GP2, they need to be large in order to get the performance that the customer needed. In this case, 6,000 IOPS for some of these workloads. So they needed to artificially make them really large to get that performance. But the other thing was they had a lot of duplicate data. And so what we immediately talked about is the fact that we don't need to make multiple copies of this data and spread it all over the place and have all these EBS volumes with the same data in order to consume that from the application. What we could do is move this into a shared file service that's already cloud native, already has hooks into Kubernetes, and make it very simple when a pod gets scheduled to use that file system and share the same data between any and all pods that need to take advantage of that, not only locally within the same availability zone, but even across AZs. And I'll talk about that use case in a second, why that's important, particularly for the way that most customers deploy Kubernetes clusters in the cloud today. The other aspect that we found with this customer that I want to point out is the fact that they had a lot of unattached volumes that they were paying for every month. And this was simply a fact of deploying them, using static provisioning, not having a good cleanup mechanism in place to delete those upon the unscheduling of the pod, which resulted in a bunch of stranded EBS volumes that the customer didn't know about, didn't realize they were paying for, and had data in them that nobody knew what it was. So this is another opportunity for efficiency and cost optimization by looking for those stranded volumes that may not be any longer associated with running applications and cleaning those up, and ideally moving them into a file system where this wouldn't be an issue. So modern applications need durable shared storage. So I've talked about the data sharing example. Lots of applications need to be able to share data for different use cases. When we're talking about machine learning, when we're talking about analytics, a lot of times we need access to the same data set, and file systems are great for that. From an availability and durability perspective, we want to build resilient applications. And as I mentioned, customers are deploying clusters across AZs now to give them maximum horizontal spread and availability and resource utilization. And we want to do the same thing with the storage. So having a file system that can span not only multiple compute instances, but across availability zones offers an enhanced availability, not only from the perspective of failing over, but from an active perspective, so that all compute instances can access the same data regardless of where they happen to be scheduled within a region. And then lastly, from a scalability perspective, we want to be able to scale not only horizontally, but also vertically for big data sets. And again, use cases like analytics, machine learning, big data, all of these things require that we can grow beyond some of the traditional limits of individual block volumes and into a highly scalable file system that has petabytes of scalability. So when do containers need shared file storage? Well, long-running workloads, right? This isn't for transient workloads, but for things that need to basically run a critical application or an application that needs to maintain state, and those that need to share data with each other. So we talked about some of these use cases already. Some additional ones that I didn't touch on are like Jupyter notebooks, which becomes really important when we're doing ML and AI and that type of thing. All right, so let's talk a little bit about EFS, and then I'd love to actually show you this in action. So EFS is our Elastic File Service, and it provides, not only a shared storage solution for modern applications that run in containers, whether that be in Kubernetes or on a different platform, but it also gives us not only high availability, but active access across multiple node groups, across availability zones, and even across regions. And I'll talk about that now with our new replication enhancements that we have brought into the service. So this becomes really important from a persistence perspective, but we also have some great benefits when it comes to how EFS manages data and how it scales. So number one, it's fully managed. So I talked a little bit at the top of the presentation about our layer of abstraction with EKS and the fact that the control plane is fully managed by AWS. You don't have to manage that at all as a customer. That undifferentiated heavy lifting is done by us. Same is true with EFS. So if you look at the file system, what you're going to see is you can choose the capacity, you can determine how much performance you need, but you're not managing any underlying infrastructure. This isn't a NAS server that you have to patch and update and grow and add memory to, or any of those types of things. And it's simply fully managed. It's a file system and you can use it. From a growth perspective, and maybe arguably more importantly, a shrinking perspective, it's fully elastic. So it is our file service that grows and shrinks with you. You can spin it up and not put any data on it and not pay for it. And as you consume data, you will pay for what you're using, and no more and no less. So this has been one of the tenets of EFS for a while. And most recently, we've extended that not only from a capacity perspective, but into performance as well. And this becomes really important when we're talking about choosing how much throughput a file system needs to be able to have to accommodate workloads that are running these persistent applications. So whereas before we needed to make a choice, how much throughput is the maximum that we need to provision so that we never run out of performance, or we had this older concept where we had to, much like the old GP2 volumes, accumulate performance by capacity. So the more data you had in it, the more performance you got. And customers would do silly things like add more data than they needed just so that they could get additional throughput. So all of that has changed now with the addition of this elastic throughput feature, which now allows you to pay for just what you're using, which is a great use case for these modern applications. And then lastly, from a performance perspective, from a cost perspective, we have added some cost optimization capabilities by way of intelligent tiering. So a couple years ago, we introduced a new tier of storage to the standard tier, which was an infrequent access tier, much like our S3 infrequent access. And just this last year at reInvent, we also added an archive tier, which makes the dollar per gigabyte significantly less. So just to break this down a little bit, from a performance perspective, one thing that we've done over the last really year and a half to 2 years is take a look at EFS performance. And I always like to talk to customers about this because it's been around for such a long time, many customers have tried EFS in the past and found it to be lacking in terms of their use cases. As I mentioned before, it was a file service. It was a file share that we introduced for those workloads that needed to be able to share Linux data between one another. And it wasn't necessarily much more than that. And as we saw customers using it for application data and production workloads, there really became a need to focus on performance optimization. So 2 years ago, we introduced a 2x improvement in both read and write latency. And then about a year ago, we introduced a 3x increase in throughput. So you can see we can do 10 gigabytes per second for reads and 3 gigabytes per second per writes. And again, keep in mind, this is all active across multiple availability zones, multi-readers, multi-writers. So we're able to get that performance. And then most recently, at last reInvent, we also increased the IOPS by 4.5 times. So now we can get 250,000 reads from a single EFS file system and 50,000 write IOPS. So it's definitely come a long way from the early days, and we're seeing the adoption for these use cases by many of our customers for that reason. I mentioned elastic throughput. This is now the default option when you provision a file system, which again takes away that burden of having to make a lot of choices when it comes to the throughput performance of the file system. You can simply pay for what you need, and you have the peace of mind and the assurance that you'll have the performance when you need it. I talked about the fact that this is multi-active. So this is really important to understand, particularly if we're architecting for resiliency and high availability. So we have a 4 nines SLA for availability, and we're also designed for 11 nines of durability. So if anybody has been around S3 for a while, that's the same 11 nines of durability that we've always had with S3. The same is true of EFS. And from an availability perspective, as I mentioned, not only does this allow you to build redundancy into your applications, knowing that you can tolerate the loss of access to an AZ and maintain access for your cluster, but it also allows you to spread things wide. And I'll show you that in the demo in just a minute, why that becomes important as we're architecting these scale out, horizontal type of deployment workloads. We also have a built-in backup mechanism, which I'll talk about in a minute as well. But before I do that, I want to talk about replication. So replication is something that customers have been asking for a while now for EFS, because again, as customers want to use this for mission critical applications, they're being asked to do more around compliance and data availability and going global with the global economy that we have today. The need really exists to have a native replication capability at the file system level. So you're not having to do backups and restores of data like some of my customers have had to do, particularly on the Kubernetes side with third-party or open source tools to be able to bring up data in a secondary region. But now with native replication, we can simply point the file system to a different region and either create a brand new file system on demand as part of that replication automation, or as we just introduced also at reInvent, point that at an existing file system. So if you want to have replication between two file systems running in different regions, you can do that simply by creating a replication relationship between them. This also enables a capability called replication failback. So if you're wanting to fail over your, let's say, Kubernetes environment from region 1 to region 2, you want to bring up those pods in the second region that are stateful, you want to access those, test them, validate them, or in the case that you're actually in a true DR scenario, you want to run business from that region for a while. New data gets written at that site as the data, as the file system becomes read-writable. and now you want to synchronize that back to the original production side. Well, fail back allows you to point back at that original file system, replicate the data in that direction, and now you don't have to reassociate all of those existing applications of workloads with a different file system. You can simply just replicate the data back and easily fail back to the production side. And then lastly, I mentioned backups. We have integrated backups with EFS that run on a managed schedule if you want. You also have the ability of controlling that. And they also tier the data, which is a nice ability that EFS has to cost optimize not only the primary storage using intelligent tiering, but also the backup storage. So we can tier that between warm storage and cold storage, depending on the age of the backup, so that we're constantly cost optimizing the data so that you're not paying more than you need to, which makes it achievable to use this as your persistent data layer. And then the new archiving feature that I mentioned, which was new as of reInvent, takes that cost savings that we got with our infrequent access tier and extends that from 1.6 cents per gigabyte per month to 0.8 cents per gigabyte per month, which is astoundingly cheap for file storage running in the cloud. So this is a great way of maintaining data, holding it long term, not having to delete it if that has business value and you want to just have it on a lower class storage or a lower tier within EFS. And then the great thing is, from a performance perspective, if that data is accessed, it could either be accessed on first read and moved back into the standard tier, or you can set that to actually stay in the archive tier or have a pattern of access before it actually moves. So that's all tunable based on the intelligent tiering policies that you control. All right, one more thing, and then we'll shift into demo mode. So many of our customers build applications in the cloud, and other customers want to take existing workloads and existing applications and modernize them and move them to cloud. So EFS becomes a really good scenario for this, for those applications that might be running on compute infrastructure and storage infrastructure in a data center. And without having to retool and replatform all of this, as you're trying to migrate, we can take a stepped approach. And so by using EFS as that kind of landing zone for data, we can use tools like Amazon Data Sync to move data from whatever NAS server or storage array that might be running in a data center into EFS. And then once it's there, you can start that journey and process of modernization by simply pointing at that file system and accessing that data, whether that's using a machine learning use case with something like SageMaker, or in these microservices examples, running on EKS or ECS and using serverless compute or traditional EC2 instances. All of that becomes possible if the data is already in a service like EFS. All right, now demo time. So I always like to say, a picture, if a picture's worth 1,000 words, then I think a demo is probably at least worth 1,000,000, because I think it's really helpful to see what some of this stuff looks like, and at least for me, getting hands-on with it really solidifies some of these concepts. So this is my Sandbox account, and I've got a couple of instances that I'm running that are part of a 2-node EKS cluster. And these 2 instances happen to be running in separate availability zones within my production region, which in this case is up in Oregon. As I mentioned, this is a design pattern for many customers when it comes to deploying Kubernetes in EKS. You want to spread this across multiple failure domains, across availability zones, so that you have not only the distribution of resources, but you have access to services that might be running in different zones. And so we want to be able to extend that with storage as well. So the first example I'm going to show here is what it would look like to deploy a stateful application using EBS. And as I mentioned, this is the most common thing we see when we look at how customers are deploying these persistent volumes today. So to demonstrate this, I'm going to go ahead and launch a couple of pods. And before I can do that, I need to look at what storage services I have available, what storage classes, rather, I have available running in my cluster. So I'll use kubectl to do a get storage class or a get SC to see what's available. And as I mentioned before, we have this GP2 default storage class. And this is really, again, to allow customers to be backwards compatible if they've got older versions of Kubernetes, if they've got older versions of EBS. We always want to be able to facilitate that and allow them to use that. But the problem here is that this is using an old version of the provisioner, which is no longer supported by Kubernetes. And so we've moved on to this new modern approach of a CSI driver rather than an in-tree provisioner. So the CSI driver is basically a container storage interface. It's very easy to install. In the case of both EBS and EFS, we can use it as a EKS add-in or add-on, which is very easy to add on to the cluster with just a simple line of code. And if we're running the CSI driver, we now have the ability of upgrading our storage class to use a different storage class. And in this case, we're going to use this one, which is this EBS storage class. If you're looking to do this on your own, you can simply go to the repo on GitHub for the EBS CSI driver, and you can grab all these YAML files in the examples folder and download this. And this is basically all it's doing is it's saying we're going to create a new storage class called EBS storage class, and we're going to use GP3 as our default EBS type. So let me go ahead and deploy this now. And now what we'll see is if we do a get storage class, we have two options. We've got our default GP2, and now we have this new one, which is using the EBS CSI driver, which is what we want. So in order to use the storage class, we need to create a persistent volume claim. Now, I'm not going to get into the nuances of static provisioning versus dynamic provisioning, but just suffice to say, dynamic provisioning is what many customers do who are running CI/CD pipelines and want to abstract things and use automation to very easily deploy resources like storage without having to involve administrators to create volumes and map those volumes or those PVs to persistent volume claims, which is what developers put in their YAML code when they're launching an application. So, sorry, let me get rid of that. So in order to do that, let's go ahead and look at this YAML for our EBS claim. And as you can see, this is just a simple claim. It's set to read write once because this is a block storage volume and we don't want to get into a data corruption scenario by trying to use multiple writers that aren't supported by EBS because we can't do things like file locking, which we can do with the file system. So I'm going to go ahead and deploy this claim. And before I do that, I'm just going to go back to the console real quickly and click on the volumes tab. And you'll see I have two EBS volumes that are already associated with this cluster and these instances. And these are just running the root volumes for those EC2 instances on the compute nodes as part of that Kubernetes node group. So now when we go ahead and schedule, oh, excuse me. When we schedule this new PVC, we can do a get PVC, and you'll see that it's going to be in a pending state. And the reason for that, if you go back to the storage class, you can see that we're in this volume binding mode that says wait for first customer. So with EBS, we don't want to have storage sitting out there costing the customer money that's not being actually consumed by an application or used by any workload. So by design, it's a good design pattern to have it set this way so that you're not stranding a bunch of EBS volumes out there that you're paying for and having to get a bill for that when it's not actually doing anything. So in order to use this, I'm going to go ahead and schedule my first pod, which in this case is just running a CentOS application. It's going to mount storage using this /data path, and it's going to point at this EBS claim. Now, you'll notice one other thing that I've done here is I've used a node selector, and this is just for the purposes of this demo. This can be explicitly set if you are, trying to maintain affinity rules when you're scheduling pods on different instances in Kubernetes. But in this use case, I want to make sure that we're using a node selector to demonstrate what happens when pods get scheduled, whether intentionally or simply by way of resource utilization on different instances within the cluster. Because pods are using shared resources like instances, you technically could have multiple pods on the same instance using the same EBS volume. But if those pods are scheduled on different instances, which often occurs, then we start to get into some issues. And I'm going to demonstrate that really quickly here by showing what happens when I schedule this pod. So we'll schedule pod 1. All right, so before we look at the pod, let's go back and we'll look at the PVC. And what should happen in just a second, as you can see, is we go from appending to bound. And in fact, when I go back here to the console view and hit refresh, we have a brand new EBS volume that exists that was dynamically provisioned and now has 4 gigabytes of capacity using GP3 storage. So that's an example of how dynamic provisioning works with EBS using the CSI driver. Now let's do one more thing here, and imagine we want to schedule a second pod that just so happens to land on a different node within the cluster. Now, as I mentioned before, this node happens to be in a different availability zone, but the same concept would apply regardless of where this actually lives inside of the cluster, and you'll see why in just a second. But I'll schedule this second pod, pod 2. Let's see, apply would be a better thing to type there. All right, so now we've got a second pod. And now if we do a get pods, you can see we have one running pod running app 1, and we have one pending pod running app 2. Now remember, we're looking for the same EBS volume, and this is going to cause problems for us. If we do a describe command and we say describe pod app 2, let's see what's going on. Why won't it schedule? Well, of course, the reason it's not scheduling is because one node didn't match the affinity rules. So this would be perfectly fine if these were stateful pods that we were launching, meaning that there's no persistent volume claims, because it doesn't matter. We can use any CPU and memory resource provided that the instance has those available, and Kubernetes will help determine that. But as soon as we anchor that application down to a storage resource like EBS, now there's a dependency in play. And it just so happens that because this EBS volume is already owned by the pod running on the first instance, now we can't schedule it on another instance because that EBS volume doesn't have the ability to be attached to that second instance, and it certainly doesn't have the ability to be attached to an instance running in a different availability zone. So what do we do if we need to share data? Well, as we already talked about, we've got this other option here called EFS. And I'll really quickly show you the storage class for EFS. We've got a bunch of other mounting options here because this is a file system. It's a little bit more complex than just a simple block storage volume. But I have this file system ID. Now, if you have done this in the past and you've used static provisioning, there's a few more things you need here. You need an access point and an FSAP, which is the file system access point ID. But we're not doing that. We're going to use dynamic provisioning. Again, in the spirit of being DevOps and using pipelines and automation and being able to pass variables and do things in a very on-demand type of way, we want to simply have a file system that we point at and let the software take care of the rest. So if I look at the EFS service running in my region, you can see I've got one file system called EFS prod. And if I click on access points, there's no access points that exist yet. So let's go ahead and deploy this EFS storage class. And now when we do a get SC, we can see that now we have a third option, which is this EFS storage class using the EFS CSI driver, which I already have running on the cluster. All right, next step again is to create a claim. Now this can be part of your pod manifest if you want, but let's just imagine a developer needs to request storage for an application. We're going to do that again. Now we can use read write many mode because we can have multiple readers and writers. It's a fully POSIX compliant file system. All the file locking is managed by the file system, so there's no issue mounting this as read write. In fact, we're going to not only have it read write for the application, but we can make it read writable across multiple AZs via mount targets that EFS puts in each of the AZs that we deploy it into. So this makes it a great scalable storage service for this type of use case. So I'm going to go ahead and apply this claim. All right, and now we'll do a get PVC one more time, and we have now a second PVC that's bound. And if we go back to our console view and hit refresh, we should see a new access point was automatically created with dynamic provisioning. It's got a path name, which, by the way, if you're using this with replication, we have a new enhancement to allow you to reuse the same path, which was a limitation of dynamic provisioning in the past that the new CSI driver supports. So if you wanted to take this volume, mount it in a cluster running in a completely different region, and launch pods using the same YAML manifests and pointing at the same directory paths, we can do that, and that gives you a very easy way to bring up replicated data that's managed by EFS on the back end. All right, last thing we'll do here is go ahead and schedule our first application, which is going to be pod 1. All right, there it is. It's running. And while we're at it, let's go ahead and just do the same thing for pod 2, which again, I've got a node selector telling it to schedule it on the other node just to show that we can do this across nodes and we can do this across availability zones. All right, so unlike our EBS example, now we have two applications running on two different instances on two different AZs using the same PVC. So in fact, if I want to do that, I can even do a -O wide, and you can see that in fact these are actually running on different nodes. All right, last thing, just to kind of finalize this and show the, you know, the punctuation at the end, let's go ahead and write some data and then read it from the other end. So I'll do that by doing a kubectl exec, and let's go into our first one, which was EFS app. Maybe it was EFS app 1. There it is. And let's just go into that data directory that we created, and we'll create a new file, and we'll just echo the phrase node 1 data. And we'll save that into a file called node1.txt. There it is, node 1 data. And so we created this again from app 1 running on AZ1. So let's go ahead now and do the same thing, only this time we're going to go in to app 2, which we know is running on the instance in the other AZ. We will go to the data directory, and we'll see that in fact there's our same file, and we can read it. And in fact, if we wanted to, we could create a new file as well because it's read writable, no issues. And so there you go. I think this is a real simple example. Obviously, there's a lot of more sophisticated use cases that we could demonstrate with machine learning workloads and analytics and other tools that customers are using all the time to be able to do these things in Kubernetes and in EKS. But I wanted to just finish up today by inviting you, if you would like to have a hands-on experience and play with some of the tools that I just demoed, you can do that by going to eksworkshop.com or hit that QR code, it will take you directly to the storage modules that we've built, one of which is the EFS module that takes you through a similar example to what I just showed you, although it's a little bit more interesting than what I just did with some static files. So with all of that, I would like to thank you for your time. I really appreciate you spending an hour with us today. And I would like to just, again, invite you to check out more by either visiting the workshop or going to our website, and we'd be happy to engage with you there and answer any additional questions that you may have about persistent data and optimization on Amazon EKS.